This is a demonstration of the remote sensing elements of the Protection Range Estimator software. This video builds on background information available in other videos on this website and in various published articles. Here we have the spectrum analyzer display of the Protection Range Estimator software, and it's showing one pilot signal right here, but we could have two pilot signals or three pilot signals, but we'll start with one pilot signal. Let's turn on the genetic algorithm display. The purpose of the genetic algorithm unit in the software is to estimate four parameters of the IED attack scenario. The first parameter is the height of the ECM transmit antenna. The second parameter is the height of the Protection Range Estimator device's antenna, which we'll call the sensor antenna. The third parameter is the range between the ECM transmit antenna and the sensor antenna. And lastly, the relative gain of the ECM antenna, and that's relative to the gain of the sensor antenna. There are four elements in this display which summarize the output of a genetic algorithm-based estimator, so let's go through them counterclockwise, starting on the left. On the left side we have a graph of the probability density functions for the ECM transmit antenna height, that's shown in yellow, and for the sensor antenna height, which is shown in light blue. Engineers love graphs, but you never show a graph without explaining what the axes are, so I'll do that. The vertical axis is the antenna height, and the horizontal axis is the probability that the genetic algorithm estimator will indicate a particular height. And right now, neither antenna height is being estimated. The ground truth values are being passed into the software. At the bottom, we have the probability density function of the ECM to sensor antenna range. The horizontal axis is the distance between the ECM transmit antenna and the sensor antenna, and the vertical axis is the probability that the genetic algorithm estimator will indicate a particular range. And again, right now, the range is not being estimated, so it's just showing the ground truth value, which is 24 meters. On the right side is a graph of the probability density function of the ECM transmit antenna gain. The vertical axis is the antenna gain, and the horizontal axis is, again, probability of observing a particular output from the genetic algorithms. And again, this parameter is not being estimated, it's just showing the ground truth value. In the middle, we have a graph of power versus range for all the solutions that have been found by the genetic algorithms for the given observed power, a pilot signal power. The vertical axis is received power and the horizontal axis is range, and the little red icon in the middle is the current pilot signal power that's measured by the Protection Range Estimator device, in other words, the sensor. Now, the genetic algorithms can be made to estimate any combination of these four unknown parameters. So let's start by trying to estimate the height of the ECM transmit antenna. Let me just click a checkbox there, and now that's on. Okay, immediately we see that the probability density function of the ECM transmit antenna now has three signals in it. That's three yellow peaks. And the power versus range graphs in the middle show three distinct solutions. Now, one of those solutions corresponds to the true ECM antenna height. That's 2.5 meters. Also notice this gate structure hovering around the probability density function. The center dashed line is the estimated antenna height, and the box around it represents the standard deviation of the probability density function. It's only got two signals in it right now. Now let's take a closer look at the power versus range graphs, and I'll change the scale so you can see them a little bit better. Here we see all the solutions that are produced by the genetic algorithm estimator for which match the observed power at the sensor. But we're only using one pilot signal frequency at 1809.2 megahertz, so let's turn on a second pilot signal, like this. Now we're measuring the power at the sensor at two different frequencies, and since both signals use the same physical path, the genetic algorithms, along with by using a propagation model, deduce that there's only one possible answer for the ECM transmit antenna height, and it's the correct height, 2.50 meters. So let's go back to using one pilot signal for the moment and try to estimate the sensor antenna height as well. Instead of just estimating one height, we'll estimate them both. Okay, several things are happening here, most of which are outside the scope of this short video, but looking at the power versus range display in the middle, we can see that the genetic algorithms have identified families of solutions for which the propagation model predicts the observed measured power at the single pilot signal frequency of 1809.2 megahertz. And you can see that the probability density function on the left-hand side shows a lot of possible solutions. Many solutions are found for a single pilot signal frequency. So let's go to 2 pilot signal frequencies. Then a single family of solutions is found. And if we filter the output, we find that the estimates are quite good for the transmit and receive antenna heights. And we could use 3 pilot signals too. And if we do that, after the PDF records settle, I could reset them, and it slows the software down a lot, but the estimates settle to even better values. But let's go back to, rather than wait for this to settle, we'll just go back to 2 pilot signals. Now let's try to estimate all 4 parameters and see what happens. The range and the antenna gain. We'll reset the records. Now, the software slows down a lot, and the power versus range graphs in the middle don't make sense anymore because of the way that they're prepared. But we can see that we have quite good estimates of all 4 parameters, which persist even if we change the value. For example, let's change the range from 24 meters to closer to 50 meters. Once the density function settle, I'll reset the records. Again, we have quite good estimates of all the parameters. Let's change the transmit antenna height to, say, 3 meters, about 3 meters. That's the red line over here. Now we'll let the probability density function settle, or reset the records. And we're using 2 pilot signals here. But once again, after we let it settle, we find that the estimates are quite good, actually. We can change the sensor antenna height to, let's say, from 1.5 meters to 1 meter here. And again, you see all 4 parameters are looking quite good. I'll reset the PDF records. Just it cleans up the display, that's all. And once everything's allowed to settle, we find the answer has a slight bias in it, particularly in the antenna height estimates. But it's not a bad answer, and it's actually better than the uncertainties assumed in earlier calculations, which assess the protection range estimator's likely performance. Now, all this depends on having a propagation model that's believable. So let's go back to that. Do we believe the propagation model? This is a playback of power versus range for the spectral recordings spaced 1 meter apart across a 40-meter range flat asphalt test range. And the agreement is between the predicted power versus range, which is shown in yellow, and the measured power, spectral playbacks, at 1 meter intervals is shown in red. So it's a very good agreement. As a concluding remark, it is not the purpose of this work to estimate the relatively uninteresting case of reflection over a flat ground, although that does have its applications. The more urgent and important problem is when there are multiple spurious scatterers present. And the objective is to generalize the solution presented here to be able to sense when the local environment has compromised the ECM and then provide a warning so action can be taken either to restore the jamming protection or to move people and assets out of harm's way. And this concludes the demonstration.